Let's talk about optimizing navigation meshes, or a couple thoughts about how we could optimize the underlying data as we're generating it. So optimization of nav meshes tends to happen in a couple different places. The first thing that we might want to consider is if we're generating navigation meshes that look something like this, and we go through a process of triangulation, one thing that this would do is create edges, or potentially create edges like this. Then we create our graph data structure underlying it that looks something like this with connecting edges. And that way our AI knows how to move along this area. Well, this shape could be optimized to remove some of these edges. Now, an optimization method that we could use is called the Hertel-Melhorn algorithm, which is actually not too complex. Let's take a look at that original shape here, which looks something like this. And let's imagine it's gone through a triangulation process that looks something along these lines. The Hertel-Melhorn algorithm essentially asks the question of, for each edge, could that edge be removed? And in which case, would a convex polygon remain? So this is one method of doing convex decomposition. First you do your triangulation, and then you do this Hertel-Melhorn algorithm. In this example here, we would explore each of the internal edges. And internal edges are edges that don't have any sort of connecting polygon on the other side. If you're using a half-edge data structure, it means that there are half edges that don't have a connecting opposite edge along with them. Let's take a look at what this algorithm would do on a mesh like this. The first thing that we might do is we might explore these edges over here, in which case we would say, does this one have a half edge? Or does this one have an adjacent edge? Nope, we can't eliminate it. Does this bottom one? Nope. Does this one here? Yes, there's a connecting edge here. And now we ask ourselves the question, if we were to remove this edge and combine both polygons so that we had a larger shape that was the same shape as the two polygons connected to each other without this connecting edge, does that leave us with a convex polygon? In this case, the answer is yes. In which case, we remove this edge, and then we end up with one larger polygon. Now, it's really easy to do this by hand when I'm just drawing stuff on a whiteboard or an iPad like this, but when you're actually storing half edges and data structure for polygons, actually combining polygons may be a little bit of a tricky step here, and you may end up with like a little bit of a long function, but the gains at the end of this are actually pretty substantial, so it's worthwhile doing an optimization along these lines. So let's look at the next one. We keep exploring edges until we get to this edge up here. This edge, we would ask ourselves the question of, if we remove this edge and we were to combine these two polygons, would we end up with a convex polygon? Well, the answer is no, because we have a reflex angle right here. So we leave that edge as is. And we keep iterating through all of our edges until we find another one that has adjacent edges. This one. This one has two adjacent edges. Well, if we were to remove this edge here, does that mean that we'd be left with a convex polygon? The answer here is yes. So let's remove it. So now we actually end up with just two polygons, whereas back here, the original one was represented by 4. So we've actually cut the size of our data in half, which can be a pretty substantial gain. The underlying graph for something like this is also just 2 nodes. So now as your game is being played, every single pathfinding algorithm that goes and generates paths on this, and every single AI, whenever it goes to generate a path, can do so probably twice as fast as it used to, because you're eliminating half of these steps. So some pretty substantial gains here. Another optimization for nav meshes, so let's classify this as like a convex decomposition. So here's one thought, convex decomposition. And this was using an algorithm called ear cutting initially, and then something called the Hertel-Melhorn algorithm. Let's see if I can spell that correctly. I think it's the Hertel-Melhorn. That might be spelled incorrectly, but something very similar to this, the Hertel-Melhorn algorithm. Another optimization. This process of computing the navigation meshes and generating them based on your level is actually probably pretty complex. As your levels grow in size, your game is going to take longer and longer to be able to do this. So the ideal is that you would pre-compute this data. Pre-computing your navigation data and generating these grids and graphs and all that kind of stuff at a time when you are working in the editor, or the time when you are editing the content of your game, saves you from doing it as your world is changing or as your game is being played. If you were to do this sort of process as soon as a player plays your game, that means that whenever they load a level, it needs to run through this entire process and these optimizations and that kind of stuff. And it's essentially generating static data that's never going to change. So instead, we can make this something where, as we create a build of our game, as we or potentially even hook it up to like a function or some editor tool or something else along those lines, or whenever we go and edit a scene, we pre-compute the graph data structures, the polygons and their positions, and then we save those things out to a file as navigation mesh information. Then, when our game is actually being played, our system for pathfinding can instead just load that information off of the hard drive as opposed to calculating all this stuff again. This is another one that most games take advantage of because it is so computationally expensive to be able to do all this 2D and 3D geometry to generate this information. Another optimization is pre-computing paths. One very common thing that happens is we have a lot of AI that move from one position to another. So this is a very simple world here, but imagine the case where we had a whole bunch of different AI agents and we're building an RTS game. So I have a bunch of AI agents here and they are all in a specific formation. And I select all of them, and I tell them that I want them all to move to this position here. Right? Here they are, all, and this is their final position. One thing that this will happen, or one thing that this will cause to happen, is suddenly I will have a whole bunch of requests to my pathfinding system to essentially ask it to generate almost the exact same path. So one thing that my pathfinding system could do is it could cache the paths that it's generating, in which case the first AI to ask how to go from this mesh to this mesh, I generate this path and pre-compute it and I save that somewhere. And then the second one, when it says I want to go from here to here, I can very easily say, oh, I already calculated that. I already ran A star and I already ran and generated this data previously. Let me give you the same path. You go from this mesh to this mesh. This does have the caveats of if your game is changing or the dynamic or the data here is dynamic on what A star is using for its weights or values, it won't take those things into account. So there are some downsides to doing something like this. The final optimization, which is one that I really strongly recommend for everyone, is threading. Right? Or doing asynchronous path generation. Asynchronous path generation essentially sets up our AI so that instead of calling a function to our system to essentially say, give me the path to go from A to B, and then on the next line of code, it has that path. That requires the pathfinding system to generate that path immediately. One thing that we can do is we can build our pathfinding system so that instead of immediately returning the path, we could have it say, you know what, I will take my time and I will use unused CPU cycles to figure out what this path is that you want. And I'll do that during the downtime when something not complex is happening in the game. And then a moment later, within half a second or so, I will let you know when that path is finished being generated. This allows the AI system to offload the tasks of generating paths onto multiple threads or different CPUs, so it provides a lot of flexibility, as is with most asynchronous functionality that we add into our games. These various optimizations are all pretty much used across the board for most professional games and most larger pathfinding systems. I highly recommend exploring each one of these different methods and figuring out which ones are the best solutions for your projects.